Hi everyone, I'm Tutor Alice from Power Chemistry. I'm starting on this series whereby I'll be uploading a short question every day on Instagram account as well as Facebook and Power Chemistry website. And the next day, I'll be uploading a step-by-step explanation on how to solve the question. So we'll be starting from Ionic Equilibrium because I think most students seem to face issues in this topic. So this week it will be Ionic Equilibrium. So I'll choose a few questions that's testing on different concepts in that topic. So today we'll be going through this question on Ionic Equilibrium. And this is quite an interesting question. It tests you mainly on two concepts. First concept is diprotic and monoprotic base, as well as equivalence point. The next concept is on buffer, specifically max buffering capacity. So without further ado, let's take a look at the question. When 5 cm cube of a 0.1 mole per dm cube base is titrated against 0.1 mole per dm cube of ethanoic acid, we get the following titration curve. So over here, just a slight intro to the titration curve. So over here, the y-axis of the curve will be the pH of solution in the conical flask. And the x-axis will be the volume of the solution in the burette. Okay, so therefore, in this specific example, what we have here is you have ethanoic acid in the burette. So therefore, okay, so this is the burette, and you have ethanoic acid being added in. And in the conical flask, we have our base. Okay, so over here, let's look at when I have 0 cm cube of ethanoic acid. So this is referring to the pH. The pH in the conical flask is about 13.5. So this means that within the conical flask, you have a base of pH of 13.5. And then as I add in, drop by drop, my ethanoic acid, the pH of my solution will change. Okay, so over here, want to highlight this part, which is the region of rapid pH change. So this is known, the middle of the region of rapid pH change is known as the equivalence point. Okay, the equivalence point is a point where amount of acid added exactly neutralizes amount of base in the conical flask. So take note that this is the point where amount of acid added from burette exactly neutralizes the amount of base in conical flask. So over here, we have 10 cm cube. This means that 10 cm cube of ethanoic acid exactly neutralizes the base in the conical flask. Okay. The next thing I'd like to highlight is over here we have ethanoic acid. Take note that this is a weak acid. How do I know that? Because all organic acids are weak acids. Okay. So let's look at the question. Which of the following correctly identifies the base used and the point on the curve at which pH equals to pKa? So let's look at the base used first. So over here, looking at the options, I noticed that I have two types of base. The first type is a monoprotic base. What is a monoprotic base? It is a base where 1 mole of base dissociates to give you 1 mole of OH minus. Okay, and then I have a diprotic base. where 1 mole of BaOH2 base dissociates to give you 2 moles of OH minus. Okay, so let's take a look over here. So over here, what do I have? So in the question, I am given the volume and concentration of the base. From this information, I'm able to get the amount of base. So the amount of base will be 5/1000 comma the dm cube. That will be volume times concentration. And this will give me 0.0005 moles. So this is the amount of base that I have. Next, let's take a look at the amount of ethanoic acid that we have. So over here, I know that 10 cm cube of ethanoic acid is required to exactly neutralize the base. Hence, that would give me 10/1000 to change the volume to dm cube times the concentration, which will give me 0.001 mole of ethanoic acid. So looking at the mole ratio of the base to ethanoic acid, I have 0.0005 to 0.001 mole, which is 1:2. So looking at this tells me that most probably we are dealing with a diprotic base. Okay, so how do we know that? Let me go and talk about it in more detail. So let's use a diprotic base, barium hydroxide. So it will react with my weak acid, ethanoic acid, to give you. So over here, what do I have? I have the ethanoic ion as well as the barium ion. Together, they will come together to form a salt of CH3COO2Ba plus water. Now I have to balance this equation. On the right, I have 2 moles of CH3COO. Hence, on the left-hand side, I need to multiply the ethanoic acid by 2. This is what I will get. And then next, let me double check. Okay, I have 3 plus 1, 4 times 2, 8 plus 2, 10. 10 hydrogen atoms on the left. So therefore, I should have 10 on the right. Right now, I have 6 plus 2, 8. So therefore, I should multiply water by 2. Hence, this will balance my equation. So you notice, once I balance the equation, if I use a diprotic base, then the mole ratio of base is to acid is 1:2, which coincides with what I have. Okay, so then just to show you why is monoprotic base wrong, I'm going to write down the equation in purple. So that monoprotic base will be NaOH plus CH3COOH. This will give me CH3COO minus and Na plus. So therefore, you just give me sodium ethanoate plus water. So this is already balanced. Hence, the mole ratio is 1:1. The mole ratio of base is to acid is 1:1, and that is not 1:2. Hence, this is wrong. Okay. So therefore, I cancel out options A and C because NaOH is wrong. So I'm left with B and D. Next, let's take a look at the point where pH equals to pKa. So the point where pH equals to pKa, this rings the bell. This is the max buffering capacity. So the maximum buffering capacity. So in order to have the maximum buffering capacity, it has to be a buffer in the first place, right? So what are the criteria for a buffer? Number 1, I need either a weak acid or a weak base. If I have a weak acid, I'll need a salt containing conjugate base. If I have a weak base, I'll need a salt containing conjugate acid. Okay, so this would be weak acid and salt containing conjugate base would be my acidic buffer. And weak base with salt containing conjugate acid will be my basic buffer. Right? So then, after we get this out of the way, there comes the more complicated part. So imagine, over here this is my setup. So imagine that I know that my base is BaOH2 now. Okay, so this is a strong base. Now imagine I open up the tap here. Okay, and I let one drop of ethanoic acid drop into the solution. If that happens, what would I get in the solution? I will still have strong base. I will also have my weak acid reacting with my strong base to give me my salt, CH3COO2Ba. Will I have my acid? No, I will not, because my acid has been neutralized by barium hydroxide to form the salts. So this is the species present in the solution after I add in one drop of ethanoic acid. So let's analyze this. So barium hydroxide is a strong base, and this is a salt containing conjugate base. Okay, why is that so? What is the conjugate base? The conjugate base is CH3COO minus, right? Okay, so therefore, does this fit into the criteria of a buffer? No. Okay, it fulfills criteria 2. It has salt containing conjugate base, but it has no weak acid. Therefore, it is not a buffer. Okay, so this is the state as long as it is before equivalence point. Before equivalence point, whatever ethanoic acid I add in, it will be reacted off by the strong base to give me the salt containing conjugate base. So therefore, from one drop of ethanoic acid to just before the equivalence point, there is no buffer. So what do I have in the solution? Just strong base plus salt containing conjugate base. Okay, and then let's look at what do I have at equivalence point. So now at equivalence point. So at equivalence point, like we said, equivalence point is the point where amount of acid added exactly neutralizes the amount of base. So therefore, in this solution, I'll have no acid and no base because they exactly neutralize each other. I will only have this salt. Okay, barium ethanoate. So this is just my salt containing conjugate base. So over here, at this point, I only have salt containing conjugate base. So is that a buffer? Also, no buffer. Okay, because it doesn't have the weak acid. Then, the last situation is after equivalence point. So after equivalence point, I will have my salt containing conjugate base. And then, from the burette, I will have weak acid coming in. Now, for this weak acid coming in, there is no base to neutralize it, because at equivalence point, all the base has been neutralized already. So therefore, I will have the salt plus the weak acid, which is ethanoic acid. So hence, let's put this into perspective. This is salt containing conjugate base, and this is a weak acid. So I have both of this. So hence, this is yes, this is a buffer. Therefore, after equivalence point until, well, the end of the curve, it will be a buffer solution. Okay, so then the next question is, where is max buffering capacity? So for this kind of questions, whereby the buffer is present after equivalence point, take note that, again, I want to emphasize that this is for titration curves with buffer after equivalence point. the volume of max buffering capacity equals to 2 times of the volume required at equivalence point. So over here in this question, what is the volume required at equivalence point? It is 10. So therefore, 2 times 10 equals to 20 cm³ of weak acid. So hence, that will be point P. Hence, the answer for this question is D. Okay, so over here, I'd like to just very quickly go on to something unrelated to the question. So in this question, we went through a situation whereby we are adding something weak, a weak acid, from the burette into something strong in the conical flask. So therefore, my buffer is after equivalence point, correct? However, this is actually quite rare, right? So the one that we are more commonly experienced with dealing with is actually when I have something strong in the burette and I add it to something weak in the conical flask. Let's just explore this. So, strong base, and this is weak acid. So it's the other way around. So now the strong base is in the burette instead of the conical flask. So imagine this. When this happens, firstly your titration curve will be different. So this will be the volume of strong base added. And this will be the pH. Y-axis will be the pH and the conical flask. So at the beginning, you have the weak acid. When 0 cm³ of strong base is added, you have the weak acid. Okay, so it looks something like that. Okay. So over here, the equivalence point is here. Okay, so take note that the equivalence point of a strong base weak acid reaction, it will be more than 7. When you add in just from 1 drop of strong base until just before the equivalence point, what do I have? Okay, so in my solution, I will have my weak acid plus salt containing conjugate base. Okay, I will have no strong base because whatever strong base is being added into the weak acid, my weak acid will neutralize. So therefore, I do not have the strong base. Okay, so over here, weak acid, salt containing conjugate base. Doesn't this sound familiar? This makes up an acidic buffer. Correct? So therefore, over here, in this case, when you have something weak in the conical flask and something strong in the burette, you will have a buffer before equivalence point. Okay, so that's just all that I want to emphasize on over here. Okay, everyone, we've come to the end of the question, so hope that you have benefited from it. Also, I'd like to inform you that I'll be doing a crash course during the July holidays, and during the crash course, I'll be covering 70% of the H2 Chemistry A-level syllabus. We'll be going through the most common questions, the most common question types that will be asked during the crash course. So please feel free to go to the Power Chemistry website or Facebook page for more information. Also, we have weekly group tuition lessons. We have both online and offline. So if you're interested, please again go to Power Chemistry website to take a look. Other than that, please subscribe to our YouTube channel as well as Instagram and Facebook account so that you can be updated on our daily questions and its solutions. Thank you so much for watching. Have a good day. Bye-bye.